Hey class, welcome back. We are about to dive into chapter 7 where we're going to be learning about work and energy. So you think class has been hard so far? Well, now it's going to become a lot more work and take a lot more energy. Just kidding. Actually, well, it will take work and energy as it always does. But in fact, work and energy are topics a lot of times that people actually find a little bit simpler. The same problem-solving process is going to be necessary, but as you'll learn here in just a minute, energy is actually, and work for that matter, are actually scalar quantities. All we care about is magnitude and not direction. And that tends to make life a little bit easier in some ways. But I love work and energy. I love work and energy type problems because it's just so all-encompassing and it has so many different applications. You'll see work and energy apply to things like kinematics, to things like motion, to things with electricity, with things with magnetism. There's just so many different applications. You'll get to see it over and over again in a lot of different fields. So, what is work? That's the first question. And how will we quantify it? Well, work is really when a force acting on a body causes it to undergo some displacement. Work is then done on that object. So again, here's my tennis ball, a tennis ball. If I apply a force to it and cause it to undergo some displacement, I'm doing work on the ball. Okay, now if I hold it in place and push, no matter how hard I push, if it doesn't move, no work is being done. It feels like I'm doing work because I'm pushing hard, but if it doesn't undergo displacement, you do no work. So the work done is based on both the force being applied and the displacement undergone by the object. So an easy way to think about this is if you imagine, say there's a bunch of people here, their car runs out of gas. All right, the guy back behind the car pushing in the direction that the car is moving is going to be doing a lot of work. But his friends off to the side, if their forces are mostly perpendicular to the direction of motion, they're going to be doing little to no work. Now both of these people are probably supplying a forward force somewhat, but if you imagine if they're just pushing entirely from the side, they would be doing just as much work as this girl over here is doing as she's watching. Okay, so again, the work done is based on force in the direction of motion. All right, so as you'll see, work is based on both force and displacement. So how do we quantify work was the second question we had. Well, what you'll find is work is going to be equal to the force being applied multiplied by the displacement. If you notice, I put two parallel lines here kind of as a subscript for the force. And the reason for that is because work is going to be equal to force that is parallel to the displacement. All right, so it's the amount that force and work are, or excuse me, force and displacement are in the same direction. So if you have a force that's at an angle, then you only want the parallel component of force to figure out the actual amount of work being done. And what you'll find when you take a Newton and multiply it by a meter, when they're in the same direction, you'll get the unit for work, which is the unit of joules. Capital J represents joules. 1 joule is equal to 1 Newton multiplied by 1 meter. Keeping in mind the Newton and the meter must be in the same direction, parallel to one another. So the force must be parallel to displacement in order to do work. All right, so as I mentioned, the SI units we're going to be using are newtons multiplied by meters to give you joules. There's other units as well that you'll see. So for example, a dyne is a type of force, a unit for force. If you multiply that by a centimeter, you get an erg. All right, something you're not going to see a whole lot here in class, but it's actually pretty popular in crosswords and other things. And then using the British English units, if you take a pound of force and multiply it by a foot, then you get a creatively named foot-pound worth of work. All right, so just some different units, but again, joules is what we're going to be primarily using, so you're always going to want to convert your force to newtons and your distance to meters. So, as I mentioned, it's the amount of force in the direction of the displacement. So if you have a force like you see here, this force F at some angle, all right, then the work being done is only going to be based on the component of the force that's parallel to the displacement. So in this case, the work is only going to depend on the force multiplied by the cosine of the angle. So as you can see, the work is equal to force times the cosine of the angle. That's the component in the direction of the displacement and then multiplied by the displacement. So the perpendicular component, F sine phi, does no work on the car whatsoever. So again, for a force at some angle, the work is going to be equal to force cosine of the angle times the displacement, given that this angle here is the angle between the displacement and the force, so theta here. If you were given the complementary angle to that, then you'd have to use sine, right? Or take 90 minus the angle. So if you notice here, cosine, right? If cosine of your angle is 0, if your angle is 0 degrees, your force is entirely in the direction, so you just get a 1 and you get force times displacement. If you're 90 degrees perpendicular, then you're doing no work, right? Cosine of 90 is 0, so you get 0 work. And if it's 180, what does that mean? That means that the force is directly opposite the direction of displacement, and so you would have negative work. So when you're working against the direction of displacement, it's negative work. As you'll see later, that means you're trying to take energy out of the system rather than adding it to the system. So again, if you think of somebody lifting weights, it's kind of interesting to think about it. While you're lifting weights, you're doing work the entire time. As you push up, you're doing positive work because your force is in the direction of the displacement. But then as you let the weight come back down slowly, you're still pushing up, even though the displacement is down. In that case, you're doing negative work. You're resisting it. You're taking energy away. You're causing it to descend at a slower rate than it normally would be. So in that case, then what is doing work on the bar? Well, on the way down, gravity would be doing positive work. It's a force in the direction of displacement. When you push the bar up and you're doing positive work, gravity is doing negative work, working against you. So we'll talk about work done by gravity more later in this chapter and even to a greater extent in the next chapter. So here's a quick kind of test for you. Here's a couple diagrams of different forces. In each of these, I want you to tell me, is the force doing positive work, negative work, or 0 work? Okay, so pause it, look at the pictures, and label each of these. All right, hopefully you've done that. In this first situation, what do we got? Positive work? Yep, good. The force has a component, a parallel component, in the direction of the displacement, so it's doing positive work. What about this next situation? Well, you can see your angle is more than 90 and less than 180, or you can also observe that the force is in the opposite direction working against the displacement, so you'll know that that is negative work. And then lastly here, where your angle is 90, it's perpendicular, therefore you know 0 work is being done. Cool? So let's just do a quick example with work. So here's a package. Let's assume that it's completely frictionless and it's going to slide from where it's at the top of this ramp down to the bottom of the ramp, and the ramp has an angle beta. All right? I want you to tell me, based on this angle and this height that the package starts at, so the vertical distance it starts above the ground, based on just those two variables, I want you to quantify how much work is being done. And in doing so, I also want you to think about what is it that's actually doing work on your package. So pause it, try it out, solve in variable form, and then we'll tackle it together, okay? So if we go to tackle this problem, hopefully you paused it and figured it out. The first answer, what's doing work on the problem? Well, let's look at a free body diagram. We have a normal force perpendicular to the ramp, and we have the weight force going down the ramp. It starts at this height h, and it moves this distance d as it goes down the ramp. So what is it that's doing work? Well, the normal force is completely perpendicular to d, the displacement, right? So the normal force can't be doing any work. The only other force that must be doing work is the weight. But if you notice, the weight is mostly into the ramp. Only a small portion of it is down the ramp, and so it's only a small component of the weight that is parallel to the displacement, so it's only mg sine beta that's actually doing any work. So how do we quantify work? Well, work again is force parallel times distance. In this case, our force parallel is mg sine beta, and our distance is d. So there we go, work equals mg sine beta times d. But wait, I asked you to solve for it in terms of the height, right? So we need to substitute the height in there. Well, we don't have it here, but we know height is directly related to d through the angle beta. We know that the sine of the angle beta is going to be equal to opposite h over hypotenuse d, right? So sine beta equals h over d. So we can solve for d in order to substitute in. So d is going to be equal to h divided by sine beta. We pop that into our equation over here. Boom. And what we find is that the work then is mg sine beta times h over sine beta. Oh, wait a second. Sine beta on top, sine beta on bottom, boom, those can cancel out. And guess what we find? That the work done is just equal to mass of the package times gravity times the vertical height that it moves. What? So this box-worthy answer does not even depend on the angle of the ramp whatsoever. So what we just found, and we'll talk about in more detail as we go on, but what we just found is in the absence of friction, in the absence of any what we are going to define later as a non-conservative force, in the absence of those kinds of forces, what we find is that the work being done on the object is independent of the path that it takes. So you can either have this package move straight down a distance of h or go down this long ramp a distance of d while only moving a vertical distance of h, and you get the same amount of work being done. So in the absence of friction or other non-conservative forces, the work done on an object is independent of the path. So you can either have a situation like a steep path where you have a larger force acting on an object over a shorter distance, or you can have a very long and shallow path where you have a smaller portion of the force down the ramp acting over a longer distance, and in both situations you end up having the same amount of work being done on your object. So the work done by gravity, as we'll talk about in more detail later, is independent of path. All that matters is the vertical distance that you're moving and the mass of the object. So in both situations here, the work done by gravity is just going to be equal to mgh. Pretty cool. So before we jump in to talking about kinetic energy and talking about the work energy theorem, which is really kind of the crux of chapter 7, I want to just give you kind of a brief overview of the idea of energy altogether. So we've introduced work, now let's talk about energy. Energy is everywhere, it's all around us, and it's just incredibly important to the way the world works. If you're interested in engineering, it's going to be incredibly important to you because engineering and energy go hand in hand because it's all about manipulating, using, and changing energy from one form to another, or even getting rid of extra energy that you don't want when thinking about things like floods and other things. There's a lot of energy that you want to get rid of. If you work in renewable resources, you're trying to take energy from the wind and turn it into energy for your house. You're trying to take energy in water and turn it into energy to be used in a house. If you work with engines, you're trying to take energy stored in gasoline or oil or coal and use it to turn into electrical energy that can be used for houses, automobiles, or other things. So what are some of the different forms of energy? Some of these you've probably heard of or come across. The first kind of general category that we're going to deal with is kinetic energy. As the name implies, kinetic energy is just the energy of motion. All right, anything that's moving has energy as a result of that motion. The second kind of category of energy we're going to talk about is what's known as potential energy. So that's stored energy that's stored within an object, usually as a result of some sort of a force. Okay, so all energy that we're going to be dealing with in this class, at least at this point, is going to be either categorized as kinetic, energy of motion, or potential, some form of stored energy. All right, so some examples of potential energy: gravitational potential energy, that's stored energy as a result of the gravitational force. There's magnetic potential energy, energy stored as a result of forces from magnetic fields. You have electrochemical energy, which is like the energy that you'll find within batteries as a result of electrical chemical interactions and forces. All right, there's nuclear energy, which we'll talk about more, but nuclear energy is the energy stored within the nucleus of atoms as a result of the forces on the nucleus of the atom, the strong nuclear force, for example. You have elastic potential energy, which is stored energy in things like rubber bands or springs, are good examples of elastic potential energy. You can also have electrical energy, all right, so that's energy as a result of electric fields and moving electrons and so on. There's a potential in electric fields. For example, if you're about to turn on your light switch, right, there's that potential for energy to flow stored in the electric fields in your wires and so on. You flip the switch, connect the circuit, and boom, things immediately start flowing as a result of that potential. All right. You can also have chemical potential energy. I don't know about you, I just got done eating lunch. You may have eaten some food recently. You're taking energy stored in the bonds of different atoms and, well, molecules usually, energy stored in different molecules, and there's potential in that that you can then use and convert it into other things like kinetic energy, the energy of motion as you run around celebrating the joyousness of physics, and other things. So lastly, I'll mention that mass is also a form of potential energy. Einstein's famous equation, E equals mc squared, told us that mass is actually a form of potential energy or stored energy. If you destroy that mass, it can be converted into other forms of energy. It's actually a very important part of his theory of general relativity. So the last kind of form of energy that we will discuss in more detail, and it's really actually, I like to think of it more as a form of kinetic energy, but it's what we call thermal energy, which is the disordered energy, the energy of temperature or of heat that objects have within them. And so thermal energy is a result, the temperature that something has is actually a result of the motion of atoms at a very small scale. Atoms and molecules are all moving around, and that's a result of their temperature, which is a result of them having thermal energy. So thermal energy is really very similar to kinetic energy. It's movement, it's just a lot less organized than kinetic energy. So thermal energy is a very disordered style or type of energy, and we'll get into that a lot more in second semester physics. So what we find is we have a principle known as the principle of conservation of energy. It's a very important aspect of physics, and it's something we're going to be using all the time. It's one of my favorite concepts in physics. And what it tells us is that energy cannot be created nor destroyed. It's only converted from one form to another. So the energy in the universe, to our best of our understanding, it has been a set amount ever since God first created the heavens and the earth. So scientists like to describe how he did that as the Big Bang theory, right? But in the beginning, when God created the heavens and the earth, he brought into being all matter and all energy in the universe. And since that point, it's constantly been changing forms, but there's never been new energy being created nor old energy being destroyed. It's just constantly changing between different forms. And so it's really an amazing aspect of how God created the universe. And one of my favorite things about physics is the way in which it ties so closely to my own faith. So I just threw this up here for you guys to take a minute and maybe think about. I'd encourage you to pause it or maybe talk to friends, or you're welcome to email me and we can converse about it a little bit. But I think it's very interesting in all that you do and all that you learn. I think it's always really important to think about how what you're learning integrates or intersects with your own personal faith. And so I want you to take a minute and think about conservation of energy. That's a big deal. It's a huge topic. And thinking about who God is and who you know him to be, what does it make you think of when you think about this idea that energy is neither created nor destroyed? The amount of energy in the universe has been the same since the origin of the universe. And what does that make you think about who God is? Anyway, just take a minute, think about it, and then, yeah, talk to some others. But I'm going to move on for now. I love talking about it, so let me know if you'd like to discuss. Anyway, what I want to do now is I want to link together the two main ideas we've talked about, which is the idea of work with the idea of energy. Okay, so let's see how they can relate to one another. So let's think about some object is experiencing a net force, all right? And that net force, we're going to say, is in the direction of its displacement. That net force, in fact, is going to cause it to experience some displacement. So work is being done, right? The work is simply the net force multiplied by the displacement. Now, if you recall, Newton's second law tells us net force equals mass multiplied by acceleration, okay? So I'm going to put these ideas together. And what you find is if you take work and set it equal to mass times acceleration times displacement, which is just net force times displacement, right? If you look at our equations of motion, right? Acceleration multiplied by displacement, well, that's from one of our equations of motion. So you can actually do a substitution here, divide by 2 to get rid of this 2 and move the v initial square to the opposite side. And what you find is acceleration multiplied by displacement from that equation of motion can be defined as being equal to 1/2 final velocity squared minus initial velocity squared. So substituting that into my work equation, what we find, and again, this is a little derivation. If it's a little too fast for you, let me know and I can clarify more. But what you find is that the work being done on some object as a result of some net force is equal to 1/2 the mass times its final velocity squared minus 1/2 the mass times its initial velocity squared. And guess what? Kinetic energy that we just talked about is defined as being equal to 1/2 mass times velocity squared. So, whoa, wait a second. Work equals, what is this? Looks like work equals change in kinetic energy. And that, my friends, is the work energy theorem. What it tells us is the work being done on an object as a result of some net external force will be equal to that object's change in kinetic energy. All right, so work, what does it do? Well, it causes a change in kinetic energy. Work being done on an object results in a change in its kinetic energy. And the amount of work being added is equal to the amount of kinetic energy change that the object experiences. So if you're doing positive work, it will gain kinetic energy. If you do negative work, it will lose kinetic energy. All right? So again, work is equal to change in kinetic energy. Very powerful. We're going to be using this a lot, so get used to it and let me know if you have any questions on it. So let's look at just kind of a quick and simple example here. So let's say that we have this space probe here. All right, so it's experiencing some force, a thrust force, and it's not very big, right? It's trying to conserve fuel, so it's going to have a force of 56 millinewtons. That's it. All right, and the probe has a mass of 474 kilograms. So it's a pretty big deal, right? If it's at some velocity of 275 meters per second, and while you're applying the thrust, it covers a very large distance of 2.42 times 10 to the 9th power meters, how fast is it going at the end? So maybe thinking back to the last chapter, well, chapter 6, right? Thinking back to chapter 6, maybe we're trying to adjust the orbit of this satellite, right? We're trying to have it orbit at a different distance away from the Earth, so we're changing its speed to give it a different distance, right? So I want you to try to solve this problem. Go ahead, pause the video, and give it a go. All right, so hopefully you've solved this problem, and let's go ahead and see if you did it correctly. So we're going to use the work energy theorem, as you probably guessed. Work equals change in kinetic energy. And if you remember, work is equal to the net force times the cosine of the angle multiplied by displacement, right? The net force in the direction of the displacement. In this case, our angle is going to be 0, so that'll make our life easier. Since our angle is 0, cosine of 0 is 1, so we're just going to have force times displacement. But I put this cosine in there just to remind you, you always need to make sure that you're looking at the force in the direction of displacement. So we know the force, we're given that, we know the angle, we know the displacement, we know the mass, and we know the initial velocity. So from there, we just do some algebra to solve for the final velocity, right? Plugging in, there's my force, my distance, my mass, and my initial velocity. Doing the math. Before we do, actually, if we look, hey, we know that we're doing positive work, right? So what's going to happen to the velocity? Is it going to speed up or slow down? Well, if we're doing positive work, we should be adding energy, which means it should be gaining kinetic energy, which means it should be moving faster since there's no change in mass. So I solve for velocity with a little bit of algebra, plug and chug, and the new speed that it's moving at is 805 meters per second. Boom, box worthy. All right, so look, even got my box worthy shirt on. So see how that example works? Good. All right, so I'm going to pause the video here in a second, or I'm going to stop this video and move on to a new video for the last couple concepts. But before I do, I have one more conceptual question. All right, so I've never been in an ice boat race or anything. I've never actually been on an ice boat, but they seem pretty cool. Basically, it's kind of like a sailboat with big ice skates so that it can move on ice as a result of wind. Pretty cool, right? So here's two ice boats. The blue one has double the mass of the red one, and they both, though, have pretty much identically sized and shaped sails. They look like scales to me, apparently. Anyway, they have identical sails, let's say. All right, so they're going to both experience the same force because they have identical sails catching the same wind. If they both experience the same force, I want you to answer two questions. One, which boat will have more kinetic energy when it gets to the end? And two, which of the two boats will finish first? Let's assume that they start from rest, since it's a race where they're just going to begin here and have to finish here. So think about it, maybe pause it. I want you to write down your guess, commit to your guess, and then we'll talk about it. Okay, ready? Pause, go, good. All right, so Drum roll, which boat will have the most kinetic energy when it crosses the finish line? Believe it or not, they will have the same amount of kinetic energy. How do I know that? Wait a second. One's more massive, one's less massive, Doesn't matter, right? Work equals changing kinetic energy. Work equals force times distance. They're both experiencing the exact same force. They're both traveling the exact same distance. So they both will experience the same change in kinetic energy. And if they start at rest with zero velocity, they have zero kinetic energy when they start, they both end with the same kinetic energy. That seems weird though. What's the deal? Then what's with the different masses? Well, something will be affected, right? I asked you also which one will finish first. And that's where the mass comes in, right? The lighter boat experiencing the same force will experience a greater acceleration. So therefore it will get to the finish line first, but when it gets there, its kinetic energy will be same as the second boat. Okay, so the second boat will finish last, or the blue boat, the two-mass boat, double-mass boat, will finish last, whereas the lighter boat will finish first, but they'll have the same kinetic energy. Cool. So hopefully that helps. An introduction to work energy and the work energy theorem. I'm going to stop the video, and in the second half of chapter 7, we're going to jump into talking about work being done by variable forces and some examples of that, as well as the concept of power. Have a good day.